Today I'm going to demonstrate how to use user creep routines in ANSYS Workbench Mechanical using /UPF procedure. We can start with a one element test case. For example, here is a 1 by 1 by 1 unit cube which is subjected to 0.1% strain. This is made up of with Young's modulus of 200 gigapascal. So when this is subjected to 0.1% of strain, we are going to get stress of 200 MPa, and we are assuming the in creep strain with respect to time is going to follow this equation. It's possible for us to analytically calculate what is change in creep strain as a function of time. For example, here which has two constants, one is k and another one is n, and the creep strain is function of, let's say, von Mises stress. Now it is possible for us to calculate the creep strain for various time points. Example, here is my k value multiplied by stress times power of n. Okay, to start any creep phenomena, we need to have a initial stress in the structure. So the initial stress here is 200 MPa. So after some time, let's say for after 10 hours, there is certain amount of creep strain developed, which is nothing but the initial creep strain into, we have to move this dt other side, so it is going to be this function multiplied by change in time. Okay, so accordingly there will be a relaxation in the creep, so the initial stress of 200 MPa is going to relaxed. We can develop the whole thing. We could plot the creep strain that is coming from here like this. Whole column, this blue color curve. This is a creep strain analytically calculated. We are going to compare that against ANSYS creep strain, which we got by implementing this creep law. Okay. In same way, we can compare analytically calculated stress and the stress relaxation that we predicted from ANSYS. So understand what is the procedure we need to follow to incorporate any user programmable feature or UPF /UPF capability that is available in ANSYS. First requirement is to install Photon compiler and Visual Studio. To understand what version of Visual Studio and Photon compiler is required, go to the help manual for appropriate version. I'm here demonstrating version 17.1. Okay, I'm opening the help manual of 17.1. Go to installation licensing, Windows installation guide if you are working on a Windows platform, compiler requirement. Okay. So here for mechanical APDL and ANSYS Workbench, the requirements are nothing but Visual Studio 2012 and Photon compiler 15.0.2. You need to really install these two softwares in addition to ANSYS installed on the machine. Visual Studio installed here. I have Visual Studio Microsoft Visual Studio 2012 installed here as per the help manual recommendation. You can see. Then the Photon compiler. So Photon compiler is installed here. We can launch, this is a 64-bit machine, so we have to launch 64-bit machine in administrator mode. it's going to launch the Photon compiler. This is the Visual Studio. Okay, both are required on this machine. You can check the version of Photon compiler by typing ifort command. So this is going to give us the version. This is 15.0.2. This is a minor version 179. I don't think this minor version is going to influence very much, but this 15.0.2 is very important. Once having this installed, we need to make sure the licensing for Visual Studio and Photon compiler is appropriate. To check that, we can create a small executable, a dummy Photon program, and we can make sure this is going to work as expected. For example, in this case, I'm just going to launch my command DOS prompt again in the administrator mode. I need to keep, let's say I'm going to use this small program somewhat like this, to keep this program in a directory. After a successful compilation of Photon compiler, we can test a sample program Photon compiler. To do that, launch your Photon compiler. Small area.f file, what it is going to do is it's going to take the area as an input from user, then it's going to compute squared as an area and print it. This file is kept in this particular directory. Move to that particular directory, type ifort area.f. So now you can see in this folder there is only .f file. Now it is going to compile this program and create I didn't really move to I need to move to directory D, then type area.f. It is going to compile and produce area.exe. ifort.area.f. So it compiled and produced area.exe. Now we can test this exe. Open Windows commands prompt. Move to this particular directory. Area.exe. Everything is successful as per the program. It's going to take the input from user. Let's say it's 5. Then it's going to compute area as pi r square and going to print this out. Okay, this ensures our installation and licensing of Visual Studio and Photon compiler is correct. We close this for now. Our next task is to, let's say you have a user creep routine written for the creep law that we want. That is by dt is nothing but k naught times stress times power n. Okay, so we have developed subroutine like this. So I'm not getting into how to write exactly this subroutine. One thing it is worth for me to pointing out, our actual equation is like this, but here we are going to deal with k naught, which is very small number. Okay, e power minus 23, and the other number stresses are in the range of 200. So this equation is going to handle two very large order of magnitude of numbers. Okay, so whenever we have a very large order of magnitude of numbers, it's always a good practice to deal with log scale. So now this is the equation what we have originally. So now to deal with a large order of magnitude of difference, we can take log on either side so that this equation get modified. Then to come back to the original form, we can take another exponential of this. So this log and exponential will get cancelled out. This whole term will come inside the exponential term. Again, to compute the incremental creep strain, we can take dt other side. Okay? That is the exact equation that is implemented here. Explanation, but how to handle your actual equation numerically stable way, it's up to you. What is the best way to handle the numerics involved your constitutive equations? Okay. So usually what we do is that usually we keep user creep file inside ANSYS directory. Go to ANSYS Inc. 17.1 ANSYS, you will find a folder called custom. It is always a good practice to take a backup copy of custom folder. So I have taken up a backup folder and go to user win64. So usually we keep this .f file inside this directory and compile and link with rest of ANSYS code. Since in this example I'm going to demonstrate /UPF feature, I'm not going to keep this user creep file inside this directory. We will be calling this .f file later inside ANSYS mechanical. But however, to ensure proper linking with rest of the ANSYS code, it is good practice to do the following check. Go to compiler. To start this in administrator mode, because going to compile whatever F file that we are going to create here, and it is going to create a new ANSYS custom.exe. Since this installation folder is a C drive, create or make any changes in this folder, this Photon session will require a administrator privilege. I'm going to move my working directory, cd. We need to execute this anscust.bat. Once we execute this file, to give some message, just read that out, say continue. Is it asking me wind turbine aeroelastic library to be used? This is not our purpose in this case, so I'm saying no. Then it is going to compile. You can see the new ansys.exe created here, and also it is going to create some more files here. Okay. So this is one of the reason why we need administrative rights here. It's going to take some time to compile and link use and routine that we are going to develop with the rest of the ANSYS code. Okay, this user creep file only computes the creep strain. There is an elastic strain, there is a plastic strain, there is a whole lot of other calculation need to be done. Calculations are done using the rest of standard ANSYS subroutines. Okay, so whatever this creep strain that we need to link with rest of the creep strain. So first time it is going to take some time to run this and link the whole files. Let this run for some time. Okay, once this is run, Then it's going to say, can I copy rest of the DLL here? You can say no or yes. Now, the important thing to notice here is that the link is successful. Okay, this means that when we say this link is successful, okay, now ANSYS user creep can be linked with rest of the code. Okay, now we have made sure everything is done. These are all the prerequisites not required when we are executing the user creep routine. Let me close this now. Important point is that we need to set environment variable. Environmental variable name is ans underscore use underscore UPF. This need to be set as true. This is very important. Once we are done, we need to use this UPF code. Let me open one element model. Basically a unit cube dimension of 1 mm by 1 mm by 1 mm, and it's meshed with only one element. Okay, so that totally what we have is only one element. You can just see that the number of element is only one, and this is subjected to pure uniaxial stress state. To do that, the frictionless support is applied on the back face, bottom face, and the side face. That when we apply displacement of 0.001, produce 0.1 percentage strain along the x-axis. And we need to call the UPF. We need to place the UPF file in the solver directory of this folder. This is the UPF file, the same I was explaining earlier. Then what we are going to do is we are going to call /upf.f. creep.f. This should be same. File name has to be exactly same as user creep.f because it's going to call some of the DLLs which are predefined by ANSYS. That's the way we are going to call this. And another thing is that if you have defined any variables, we need to write out the state variable in the output file. This state variable need to be called at every load step. Okay, this step selection mode need to be set as all. The UPF can be done only once. This is only at the first step. Another thing is that in order to use the creep controls, this creep control will get activated if we have the material defined with creep material model in the engineering data. This is a structural steel. By default, it is not going to have any creep material data. You can use any one of the creep model here and put some dummy constants. That's if we don't use this dummy creep material model, we will not see the creep control get activated under analysis setting. This is an important point. Another important point is that if you are going to solve this problem in unit system, then when we are setting engineering data here, reference unit must also be in mm. Okay, we cannot set that here as meter, and here we try to solve mm, then it will it will throw some errors. Okay, so we have to define some dummy data here. Now under this body, what we are going to do is first we are going to delete the creep material data that we have defined under engineering data. Then we are going to define new user creep material model. This 100 means that we are going to call a user creep.f. So this user creep.f, as I explained, has two constants. One is k here is referred as c, and another one is n. N is referred as c2. So we are going to supply two material properties. So prop 1 corresponds to this 5.0 e power minus 23, corresponds to this 7. And also we are going to define one state variable for this material. We could define as many state variables as we want. Then thing is that we know this is supposed to produce 200 MPa stress for given 1% strain, going to act like a initial strain for the creep calculation. So we need to set up this problem in two substeps, total two substeps. The first substep, the initial condition is established only for a very small amount of time. Then the actual creep calculation is carried out for 1000 hours. Another important point here is that the unit system for time. So now when we are deriving these creep constants will have some time unit here. This 5 e power minus 23 is related to hour. What it means in the sense, whatever the number we are putting here, though it is showing this as a second, this actually corresponds to hours. If the input is given in terms of seconds, then this will actually mean this as a seconds. Usually creep is a long duration phenomena, usually go for 1000 hours, 10,000 hours, 100,000 hours and so on. Doing this calculation in second unit is really not a preferred way. Always it is preferred to be done in the hour unit system. So this 1000 need to be interpreted as 1000 hours, not as 1000 seconds, because the input is fed in terms of hours. So the second substep is done for 1000 hours. Then depending on the nonlinearity involved in the problem, we may have to switch on the large deformation effect and the minimum and maximum number of substeps. In the first substep, the creep effect is off, so that we are just establishing the initial condition. Then from second substep onward, load step onwards, we are computing the creep effects. Let me clear this data. So now we are set. We are calling this user creep.f. We can problem. This is running here. It is doing in the background is it is doing the compilation and producing all the UPF related files. These are all nothing but the user creep compilation and the link files. Okay, so you can see these files are just produced now, 2.42 they are produced. Also you can look at compile.log file to verify it is using the correct version of Photon. In case if you don't see these files getting generated here, it is an indication that for some reason linking and compilation is not happening. Go and look at the creep strain over the time. So before that, we need to make sure at the end of the first load step, that is 1 e power minus 8 time that we have given here, we are expecting stresses 200 MPa. So we are getting something close to 200 MPa here. Afterwards, it's going to relax. Look at the creep strain graph here. It is going up to, let's go and look at here. This is 2.3 e power minus 4. This is 2.29 e power minus 4. Okay, so we are very much close to this, and this the analytical stress is 153, and let's look at this. We are also here 153 now. Now I just want to demonstrate if we are making any changes in the creep law. Say for example here, now let me make this creep law slightly modified like this. Instead of this being a stress power n, let me put stress power n plus 0.5. So I'm going to update the formulas as well. Now the creep strain goes from 2 e power minus 4 to the 4.5 e power minus 4. Update this creep law to accommodate the new equation. For that, it needs to be C2 plus 0.5. Okay. New creep function. Let me go and the generated data. It's good practice when we are doing this for first time. We can say delete unneeded files no, so that all the files generated during the solution is kept here. So now if I go back to this file, all these things are there. Let me delete everything except script.f. So this is going to use this new formula. Let me run this again. See the creep strain rise to 4.67, really matching with this calculation. And also one measure stress has to relax from 200 to 106. Here in this case it relaxed from 200 to 106. For seeing the, let's say if actual procedure required is just like this. If you have made sure every time the compilation is going to work, if you want to make any changes, we can just go and make the changes in the user creep.f and we can run that. We don't want to really go through the path of running this custom.bat every time. The compilation is going to happen in the background every time we run this. Okay, so this is now produced in 2.45 and so on. So the advantage of using this procedure is we can skip doing the compilation and linking through ANSYS custom.bat, but for this to work expected, we have to first make sure everything is correctly set up in the machine. Say for example, in this case, let me show you another problem. You don't want to keep this keep all the files every time. Once you made sure everything is going to work correctly, you can say this as delete also. Okay, or let me keep this as no for time being. I want to demonstrate another effect. I'm just going to clear this data. I'm coming here. Everything except user creep.f. Let's say for example, if we don't set the environment variable, what is going to happen? Okay. Let me, I just copy this for reference. That's been deleted. I will this. Again. To close the whole workbench for any change in the environment variable to take effect. Now let's look at it. My creep.f still contains 0.2, so we should see a creep strain in the order of 4.5. Let's look at this. This is still going to call the UPF, and this again, this folder contains nothing. Let's solve this. Now you can see no files related to the Photon compilation is done. This means that this .f file is not really compiled and linked with ANSYS rest of the code at all. But I see one problem with the ANSYS UPF working. I don't expect this to show any creep strain, but it is still showing some creep strain. What I suspect is that go to this folder, mice, find user creep. This is another user creep file available in this directory. This is used to demonstrate this particular creep law. Okay, so the example that I have demonstrated is only this portion. Somehow this entire equation is already coded as a default stuff. Say for example, what I mean to say is that don't use any UPF also, still I'm going to get creep strain value. Should not really be happening, but it looks like by default somehow it is taking this particular creep law being implemented. In this case, since we don't have any temperature applied, this is exactly matching. Since there is no temperature applied, this law whatever we are using here is exactly matching. That's merely by the it has happened. But again, if we go and look at this, no compilation, but still we can see the creep strain. Mind for the same problem, if we close as well, if we make this variable active, to call this UPF. UPF still contains 0.5, so it has to be 4.25 in that range, the creep strain. Let me run this again. You can see the Photon compilation files coming in. You can see these Photon files being compiled. So using this UPF procedure doesn't mean just by including this slash UPF slash user creep.f is going to really use this .f file that we are keeping in this directory. We have to ensure ANSYS really can compile and link with rest of the program, and we need to set the variable. We can use this user creep.f that is kept inside the working directory. This is the procedure. Okay? To see the In order to see the state variables, in this example, we have used the state variable same as that of nothing but the creep string. We can just insert a user defined result and we can type s var comma 1 and we should able to see the creep string as usually. Okay, but there was a issue in version 17.1. I will demonstrate this as well. There is an issue only in the post processing, not in terms of the results. Okay. So now what I'm going to do is that I'm going to open this DB file or the RST file that is available inside this folder. Open DB file. Just going to read the RST file from this folder. Reading the last results. First make sure displacement results, it's there. Then we can go and plot variable s var comma 1. Nodal solution nsol comma s var. This is the state variable, variable number 1. This is going to give same as a creep strain. The state variables are correctly written, but there is a issue in post processing the state variable in version 17.1. Are correctly computed. Either we can load the RST file in mechanical APDL and post process the results, or we can use a command snippet like this. Say first let me explain this. If you want to contour plot the state variable for a particular set, we can just, this is going to open the RST file background inside mechanical APDL and take a PNG plot. Only that plot will be shown here, okay, for a particular time. Or at any particular point, if we want any particular node, if we want to plot the state variable as a function of time, we can plot it like this through post 26 feature. Basically what this command snippet is going to do is, it is going to open the DB file in background in mechanical APDL and going to execute this command. Instead of plotting the results on the screen, it is going to plot the result on a PNG file. That PNG file will be displayed here. This is another way of tracking the state variable change with respect to time, or contour plotting the state variable for one particular point of time. This issue is limited just with post processing in version 17.1. I hope this gives you an idea about how to implement any user creep routine with respect to this .upf file. I don't prefer using this method because we don't know what is going wrong in terms of compiling or linking. My preferred way to do this is the .f file in this directory, this Photon file, and go to compiler. To do this kind of a compilation, we should make sure all ANSYS sessions are closed. Then we can use the folder. First.bat. The moment we say yes, it is going to see it says it is compiling this user file.creep. It will compile all the .f files given in here and it will produce a new ANSYS.exe here. When if there is any issue that is happening in this file, now you will get some clue about what is going wrong in this output window. Another going to run the whole thing. Now once this ansys.exe is generated, how to call this ansys.exe? See, by this procedure we know we are linking the .f. By this procedure we will not be using this command snippet, okay, because we are compiling it there. We have to go to a tools, solver settings, running it on here, my computer advanced background, or my computer advanced. Here you have to say minus custom this entire file path. Double quotes. We have to place it here. What it is going to do, it is running the ANSYS. Instead of using the standard ansys.exe, it is going to use this custom compiled ansys.exe. Okay, now we can run as usual. Running this in a batch mode, you have to go to my computer background, advanced, you have to give custom executable batch name as this, within double quotes the entire name, but here we don't want to give that minus custom as an input, okay, for the background stuff. Then we can run. We don't want to really use this approach. I think I have covered all the stuff. Once you made sure everything is correctly set up for the first time, there is no troubleshooting or debugging is required. It is just a matter of checking. Then this method is a convenient method. At the same time, just including /UPF without having the Visual Studio, without having the Photon compiler, and making sure the compilation and linking is correct, just including this command is not going to work.